lines around here. We're really not great at that. We're actually really terrible at it. The weather guys, I don't envy them, man. It's a hard job because people are mad at you when you get it wrong. And all it is a probability game. I mean, they can only do but so much. And there's so many different like models. It's crazy. There we go. Uh-oh. There we go. I got stuck for a minute. Did you do anything fun for New Year's? Did you stay up?
I wanted to stay up, but I just slept.
You got too tired, huh?
Very too tired.
Knocked off before midnight.
Finally won first.
Oh yeah?
Yep.
Yeah? How'd you do?
I scored 1 3-pointer.
Nice. Good job, Eunice. Way to go, dude. It's excellent.
And all right, 34. 2. For property.
I got a cool gift for Christmas. It's called a bird buddy. And it's that bird feeder hanging out there right now. And what it does is it has a camera in it that takes pictures of the birds.
Which one?
It's right behind you, it's yellow. See it? It's like behind you.
Is it like a wooden box?
No, it's you probably have to stand up to see it, but it takes pictures of the birds that come visit and videos.
That yellow one?
Yeah, it takes pictures and videos of my birds, and then it sends them to an app where I can go and watch them. And then it uses AI to identify the birds. So like, here's a female cardinal I had this morning. Hey, Liz, how are you? Look at her.
Ah.
Isn't she pretty?
Yeah.
She's just see my birds. Ooh. I got a new bird feeder with a camera on it. Isn't it cool? It's so cool. You can see all like here's a that's a tufted titmouse. That's what they're called. Isn't it cute?
Yep, they are.
And look at this is a pair. That's a male and a female house finch. Yep, purple-headed house finch is what they're called. Even though they're more like red-headed in my opinion.
Looks like when was this?
This was 29 minutes ago. There's a finch and then a chickadee. Chickadee will come into frame.
It's a newest one.
Yeah, this is the newest one.
Oh, this is.
So they were just here. So
Identify which bird is it?
It will. It uses AI to identify the birds, and if it doesn't identify them, it'll tell you we can't identify this. There's the chickadee, just hopped in there. But it also takes still photos, so I can scroll through the still photos. Like there's the chickadee. See? Isn't it cool? And then you can go live, like right now. Actually, it doesn't. You have to kind of open it a second time. So, watch. We can go live.
Live.
Yeah. It takes just a minute, and it's about 6 seconds delay between the camera and the song.
Battery?
Yeah, it's got a battery and it's got a solar panel too to help charge the battery. There we go. So that's who's out there right this minute, about 6 seconds ago. Yep, that's a chickadee. So there's like a 6 second delay between
the chickadees. Yep, it's still there. It's right there.
It's still there. And if you watch that guy will fly away, fly away. 1, 2, 3, 4, 5, 6, go. See, about a 6 second delay. It's cool.
It's exactly the same.
It's so cool. I love it. It's like my new favorite thing. And it's neat because hang on, Annabelle's late. Anyway, it's it was cool because I could watch them from Virginia. We went to Virginia after Christmas and I got to watch my birds while I was in another state, which is cool. Did you have a good Christmas, good New Year's?
Yeah.
Yeah, good. What'd you do for New Year's? Anything?
I just stayed up and watched the ball drop.
Which ball did you watch? The New York one?
Yeah.
Yeah, that's the one. Right, that's the one. I had some friends who said they celebrated with, forget where it is. It's in Brazil. It's the first time zone. Let me see. Yeah, like around here, around Wild Pessoa. Because it was the furthest east in the North and South Americas, in the Americas. So it was 2 hours or something ahead of New York, and they're like, Happy New Year, Brazil. Go to bed. Like that was enough. Yeah.
I have this book called Life of Fred. Have you ever heard it?
Yeah, Life of Fred Math.
Oh yeah.
We have some. They're good.
This is book that I'm taking like pre-algebra zero,
Mhm.
zero, and it's like really fun. It also talks about science too.
I like Life of Fred. We have a couple of them. We don't have like the main course ones, but we have like there's a personal finance one and a couple of others that we have, and they're funny. They're cool, they're funny. I like them.
It's like when this dude called Fred is 5 years old and he teaches in a college.
Teaches at a college, and there's a cat, right? Isn't there a cat?
Kenji.
Kenji, that's right.
His doll.
His doll, that's what it is. It was a doll.
His doll can magically talk only to its own.
That's right. That's right. Do you ever read those, Lucy? Have you ever read Life of Fred? It's a math series, but it's set up kind of like a comic book, but not quite. And it teaches math a little differently. You look sleepy. Are you sleepy? Did you really? What were you doing? Oh. Oh, a deadline. How mature of you. How mature of you, a deadline. Oh my goodness.
Deadline.
Yeah, that's wild. What's it for?
Not for my grandmother.
Is it her birthday or something?
No, it's just a piece of art.
Oh, so what's the deadline for?
Saturday.
Just a randomly imposed deadline, like have it by this day? You don't have to have it because it's her birthday or because it's a.
Yeah.
Okay. What are you making?
Signature, like scribble.
That's so cool. You know, I love it when I get people love when I get art. I had one up for Christmas. I put it away, but I have it's a little pen drawing of a little white kitten with a little red Christmas bow that one of my students did years ago. And then when she left here, she graduated from me, she made me this. And then she wrote sweet stuff on the back. She wrote to the best teacher ever, Miss Danny Stark, which was like very much an exaggeration, but how sweet. And she put that on here for me, and I've had. Yeah, she did 3 with me, but she had already done whatever class it was that I was about to teach, so she didn't need to stay an extra year. But I had her for 3. But I knew her before then, so I had her for a long time. She's really cool. She graduated high school 2 years ago, I think. I think the same year as Cole, or maybe it was the year after Cole. It might have been the year after Cole. Hey, girls, what's shaking? Oh, thank you, ma'am. Returning the glue stick. Oopsie, that drawer is weird. Annabelle might be a minute or 2 late, but we still have a few minutes, so we'll just wait a sec. I think Cole finally went downstairs. Yes, he did. Came down to say hello. That's wrong. That's wrong, right? back for another few days before he leaves us again. He's done, he never had to touch one of the legs. No.
I like the teacher.
Did you see the Twisted Sister video I sent you? With oh. They say we're not gonna take it, basically to be really dramatic. We have a on the end of your mom. Dad, it was so funny. Okay, I have a friend. Oh my gosh, I was laughing so hard. It was so funny. Do you guys know Cole? This is Drew's big brother. This is Everly, Emerson, Lucy, and Eunice.
Yeah.
You know Yusuf.
Yeah.
That's Eunice.
And
Luce, that's Eunice. Lucy's Liam's sister, if you remember Liam at all. I think you may have met him before once or twice, but anyway.
Called like I met Cole last year.
Yeah.
Yeah.
He lives in Texas 9 months out of the year, so you guys don't get to see much of him, but he's done all these classes before too. Well, not the junior ones, but because they didn't exist when he was. Nope. All right. We are doing what subject, people? No, he asked what subject. Chemistry. Chemistry. That was your favorite. We'll give Annabelle about 3 minutes. Her mom said she's running a bit late. We still have some time, so we'll give her just a few. Let's say 2 minutes. She has pennies too. What's that? Oh, you got Girl Scout stuff? All right. Can I hang on to it until lab? I'm gonna put it up there by something I have for lab so I can take a look at it. I was waiting to see if y'all brought this because a little girl in my neighborhood went around and put flyers in everybody's mailbox. And I was like, ooh, cookies. Wait a minute. I got 2 people who might bring me cookie orders. So I waited. Girl Scout cookies. I waited. Yeah, a girl at my church used to be my dealer. And then she swapped to BSA. So now I can't get cookies from her anymore. And plus she's done. She graduated last year. She got her, I think she was the first girl to get the Eagle Scout in her troop. But yeah, so she split on that. But yeah, did you girls have a good New Year's? Yeah? Did you do anything? No? Nothing? Did you stay up till midnight? You did. Okay. Excellent. Did you get sparkling cider or anything? To cheers? No? No? Nobody does that? I always did that. You were at your music school for a party? That's fun. That's fun. How many people were there? Don't know. Not very many. So we were in Virginia for New Year's Eve, but we have a neighborhood Facebook page, and yeah, somebody in this neighborhood was letting their kids shoot off fireworks, and it landed in a neighbor's lawn and burnt all their grass in their front lawn, like set their whole front lawn on fire and burnt about half of their front yard, which is pretty bad. I'm glad it didn't land on any rooftops. Okay. Yeah. Okay. So we're going to start today. We're talking about enthalpy. And for you guys, I just kind of want you to know the general concept of enthalpy. We're going to go in depth today, but I don't want you to think you have to be responsible for every bit of it. I want you to know the general idea. I want you to be able to tell me what enthalpy is, how it can be measured, and kind of what it has to do with phase changes, state changes. Okay. And that's really the big thing for you guys. All right. So let's start, people. So enthalpy is the sum of the internal what? Energy. Very good. And the product of its pressure and volume in a thermodynamic system. And what's it deal with? Energy, again, usually in the form of heat, and it represents what?
Change.
A change. Okay, now this is the important thing, the big important thing I need you to know about enthalpy. Enthalpy is how much energy exists in a system, which is basically like a system can be anything from an object to like a chunk of a substance to a whole bunch of things put together like a car. Okay, a car can have it's a system, right? So there's lots of ways to define a system, but the enthalpy is all of the energy contained in that. But here's the thing, you cannot measure enthalpy. You can only measure the change in enthalpy. So it's only when there is a reaction or a phase change or something like that happens where you have a measurable, usually change in temperature, that you can measure enthalpy. Now, there's two words in here that are math words. You got this word right here, sum. What does sum mean?
That the addend of two numbers.
Add, when you add together. So enthalpy is when you add together all the internal energy. And then what's product mean?
It's like when a number multiplied by another number.
A product means it's multiplied. So if I said, what is the sum of 3 plus 4? What is the sum of 3 and 4? What would you say?
7.
Yeah, the sum of 3 and 4 is 7 because sum means add. But if I said, what's the product of 3 and 4? It's 12 because you're multiplying, right? So that means you're multiplying the pressure and the volume. Now, when you have a multiplication problem, remember that if you increase one of the factors, it's going to increase your product. So if we had 3, if I said the product of 3 and 4 is 12, what if I change the 4 to a 5? 3 and 5 is 15, right? Everybody understand what I'm saying there? Do you understand? Okay. All right. So keep that in mind as we go through. So what is a thermodynamic system? So it's a body of, matter and or radiation confined in what? What do we confine things in? Anybody else want to guess? Eunice?
Space.
Space by walls with defined permeabilities which separate it from its surroundings. Okay, so defined permeabilities, that's a big one. What is permeability mean? Does anybody know? So permeable means that things can pass through it. So if like one thing, one of the experiments we're going to do next year is we're going to model a cell membrane. And we're going to use a material that is semi-permeable, which means some things can pass through it and other things cannot. And you'll see a color change. There's a chemical reaction that happens. You'll see a color change to prove to you that this membrane that you have mimicked is semi-permeable. So permeable means things can pass through it. So is fabric permeable? What do you think? Fabric.
Yeah, light can pass through.
Mm-hmm. Yeah, light can pass through it. Can water pass through it? Most of the time, yeah. How about air? A lot of the time. How about glass? Is glass permeable?
No.
No, things can't. Right. So So defined permeabilities just means you know what they are. You know what can get in and out of whatever system you're dealing with. All right, so this is going to show you some examples of systems: open systems, closed systems, and what are called isolated systems. And these are quick videos, most of them today.
Depending upon the movement of matter and energy in or out of the system. First of these steps is an open system. It is a system in which there is exchange of matter as well as energy between system and surroundings. Hot coffee in an open flask, as shown in the animation, is an example of open system because it can gain or lose matter as well as energy.
So what energy is it losing?
It's losing thermal energy.
Heat, thermal energy. And what matter is it losing? What matter would a hot coffee cup on a table be losing? What's coming on?
Heat.
What's here? Water vapor, usually.
Closed in this type of system can exchange energy, but not matter with its surroundings. Hot coffee in a closed metallic container, as shown in the animation, is an example of closed system because energy can be gained or lost through the metallic walls, but not matter.
So if you lift it up, if you had a hot coffee cup under a little metal tin, okay, and you lifted up the metal tin, what would you expect to find all on the inside of that metal tin? Water, right? It would condense, right? It would get all drippy in there, right? All that water vapor would come up and hit that tin, right? But if you touch the outside of the tin, would it be hot? Yeah, it would. If you put like a can over top of a coffee cup, would it get warm? It would get warm. So you're losing that heat because that heat is getting lost into the environment, but your matter is staying in. So that's
Third type of
closed.
system is an isolated system. In this type of system can neither exchange matter nor energy with the surroundings. A perfectly sealed hot coffee cup kept inside the metallic container and lid by a sealed covering is an example of an isolated system. However, there is no perfectly isolated system anywhere.
So that's a great point. So this is like double walled coffee cups. You ever seen those, or coffee tumblers people take with them, and they're double walled. So you can use them for water, for coffee, but it keeps your coffee hot for a really, really long time because there's like a layer of air or insulating material. There's like one metal layer, and then there's like insulation and another metal layer, and you pick them up and they don't feel hot on the outside at all, but your coffee inside is nice and hot. But there's no such thing as a perfectly isolated system anywhere, because if you eventually it's going to cool down, right? And it is going through the walls. You are losing heat energy, but you expect to find all your volume of the coffee inside. So that, and same thing with like I have some tumblers that keep my water really cold. They're double walled. I can put ice in them and the ice will be in there all day. But if I leave it for a week, it's not going to stay ice, right? It's going to warm up. Yeah, it's going to melt. Yeah.
And there's one more thing. You see, like when you buy metal water bottles, there's like it'll remain the heat for 12 hours.
Yep.
And then after the 12 hours, it's gonna lose.
Exactly. It starts to lose or gain heat. Yeah, depending on. Oh, they sure do. They sure do. All right, so go on. So here we are, temperature versus heat. Hey, Annabelle, welcome back. Happy New Year.
Happy New Year. I'm sorry.
It's fine. No big deal. It's fine. Oh, thank you for pennies. Wow, I'm gonna have to make change out of these. Thank you, ma'am. All right, have a seat. But you're gonna wanna, when you get home, you're gonna wanna watch the first, like, however many minutes you are, 8 minutes of this video, okay, to make sure that you don't miss out on whatever we've already talked about. All right. Basically, we're saying we're touching on enthalpy. I want you to understand what it is. I'm going to go into detail, but I'm not going to hold you responsible for the detail. And a big point so far is that enthalpy cannot be measured. Only what can be measured? Change in enthalpy. Enthalpy is how much energy is in a system. And we talked about open, closed, and isolated systems. So you're going to want to check that out. All right, temperature is a measure of how hot or cold something is. Is that a good definition? That's a definition for like everyday stuff, everyday life, but not for science. A better definition is a measure of the average what's temperature? Who knows? Yeah.
Kinetic energy?
There you go. Your average kinetic energy in the particles of an object. So we don't want to refer to temperature in chemistry class as how hot or cold something is. We want to call it the measure of the average kinetic energy of particles in an object. So if it's about kinetic energy, then temperature is a type of energy associated with what? What's kinetic mean?
Kinetic means in motion.
In motion. So it's a type of energy associated with motion. Now, this is like a kind of a physics point, but here's the big point. It's all about motion. Because the reason you feel warm, the reason you're warm is due to molecular, at the very, very bottom of it, it's due to heat exchanges in little molecular chemical reactions, and those heat exchanges have a lot to do with how the parts of the atoms are moving. And a lot of it is actually friction, but it's friction at like a tiny level, right? So heat is the form of energy that is what between objects with different, is a form of energy that is what, Annabelle? Do we know? It's transferred between objects with different what, Annabelle, do you know? Temperature is very good. So it's also referred to as what kind of energy?
Kinetic?
Well, heat energy. Heat is referred to as heat energy or thermal energy. There we go. And here's how we measure it. We measure it in BTUs, calories, or joules. Oh boy, we can measure heat in lots of ways. We don't measure temperature that way. Remember, you do temperature in usually degrees Celsius, degrees Fahrenheit, or Kelvin, but heat we measure in BTU, calories, or joules. So in physics, the second law of thermodynamics says that heat flows naturally from an object of what kind of temperature to an object of what kind of temperature, Annabelle?
Hot, cold.
Hot to cold, and heat doesn't flow in the opposite direction of its own accord, meaning if you need to get a hot object cooler, you have to add energy to the system to do that. You have to do work on whatever that object is if you want to get something hot cool. If you touch the glass table, it is going to feel cold to you. It is the same temperature as the room. So it is 68 degrees. And it feels
like
cold
42.
because it's taking heat energy from your hand and moving it into the cooler object, which is the table. And that movement of heat energy from your hand to the cooler surface is why it feels cold to you. Yes.
Is it like when you keep a cup of coffee on a table, it goes from a higher temperature to a lower temperature?
Yes, always. Yes. Do you have a question? Or are you just looking? Okay. Molar heat capacity. Okay. I just want you to kind of know this is a thing. You're not responsible for this. The energy as heat needed to raise 1 mole of an element or compound by one, that shouldn't say degree, it should just say 1 Kelvin, which is the specific heat of a mole. So it's sometimes shown as C sub M. So you might see C sub M somewhere in a lab or whatever, and it's molar heat capacity. And it depends on the number of atoms, which means if you increase or decrease the number of atoms, you're going to get a different molar heat capacity. And this dude, where is he? That's Kelvin. If you've ever wondered what Kelvin looked like, there's Kelvin. That's him.
Kind of looks like Pendulum.
It does a little bit. You're right. Yep. So you might see this equation sometime.
Q and delta.
This is how do you figure out heat, molar heat capacity. So Q is heat, N is your number of moles, C is your molar heat capacity, which is given in joules per Kelvin per mole, joules per Kelvin mole. And then delta T is change in temperature. Because remember, anytime you see delta, that's change, right? But you see here, if you increase your number of moles, you're going to get a bigger number here, right? Or if you decrease your number of moles, that's why it depends on the number of moles, which is what it says depends on the number of atoms. Yep, straight across. Yep.
Changing delta time.
Mm-hmm. So enthalpy tells how much what was added was added or removed from a system. Do you know, Eunice?
It's change in energy.
Heat and work. So remember I said a minute ago, if you are going to take a warm object and cool it down, you're going to have to do work on it. So your enthalpy, your change in enthalpy will tell you how much work was added or removed from a system. And again, it's the product of the sum of the system's internal energy and the product of its pressure and volume, which we said before. So a change in heat gives you enthalpy.
Why don't you use E instead of Q?
What I use what?
E instead of Q.
Instead of Q? Oh, I didn't make it up. I'm not the one that chose it. Q's what's been chosen. So again, there's sum and product, and we talked about that. Add, multiply, right? All right, the energy of a system can be the enthalpy of a system can be its total, what?
Total.
It's its total energy. Energy is only measured in joules, but enthalpy is measured in both what? Joules and joules per mole, given in joules Kelvin per mole. Yeah. All right. So enthalpy is a form of, we'll just say energy. Energy exists in a state of matter, but enthalpy is always the energy between two states. We talked about this before. You can't measure enthalpy. You can only measure what? Change. So here's where it comes in, guys. This is the important point for you guys. Enthalpy is always the change between two states, because you can only measure the change in enthalpy. You can't measure the amount of energy in that water bottle or that juice bottle right there. But if you heated it up, you could measure a difference in temperature, and that gain of heat, thermal energy, is your enthalpy, okay? Because you've added energy to the system, therefore the enthalpy of the system is going to increase. So energy can only be what?
Positive.
Positive, because it's energy. You're adding energy, right?
Energy is always
But enthalpy can be positive or negative, and that's because sometimes you're taking energy out of a system.
And
So
that
that's the
is-
change in enthalpy. Yeah, so it can be negative in that case. So enthalpy is a word for energy. We've been saying that. It includes molecular potential energy as well as the exchange of heat energy between different compounds or systems. So that's kind of a summary. So here's a good graphic for you. If you put heat energy in, your enthalpy is going to increase. And if you take heat energy out, your enthalpy is going to decrease because typically compounds or objects or substances with a higher temperature have higher energy. Why? What's happening in something with a warm temperature? What's going on inside of it?
But it's like a chemical reaction.
Well,
It's gonna
what's
cool down.
temperature? It's the measure of the average kinetic energy. So it's the particles moving. So you have the warmer a substance is, the more the particles are moving. Therefore, they have more kinetic energy. So the hotter something is, the more energy it has because the particles in it are moving faster and moving more. Does that make sense?
Yes.
And the colder something is, the lower the temperature, that means there's less kinetic energy, there's less energy. Therefore, that object is going to have less enthalpy, right?
Yes.
And less kinetic energy inside. So enthalpy is heat absorbed or lost in a chemical reaction under constant pressure. We have to keep pressure involved. Pressure and volume are going to matter. And in open systems, the pressure in a system remains constant. Heat's absorbed, heat loss. There's all kinds of things that can happen when you increase or decrease enthalpy. So changes in enthalpy accompany reactions. Remember that enthalpy changes can only be what, Annabelle? Do you know?
Positive or negative?
Here we go, positive or negative. Temperature impacts enthalpy change. So often reactants and products are presented in equations at, standard what?
Kinetic.
So thermodynamic. What's the matter? Oh, let's come back to the lesson. We'll worry about your video game later. That's fine. Annabelle, come back this way. Eyes up here. Okay, there we go. All right. So you good, Lucy? All right, cool. All right, so thermodynamic. We're going to talk about thermodynamics in a minute. Standard thermodynamic temperature. Okay, this is where it's important to think about when you're doing experiments in a lab. Are you typically inside, outside? Inside, typically. Yeah, typically inside. And there is kind of what we consider something called room temperature. You ever heard room temperature?
Yeah.
Like you'll hear it when you're doing a recipe, room temperature butter, or sometimes you'll hear room temperature eggs if you're making meringue, for example. You want your egg whites at room temperature. So that is what standard thermodynamic temperature is. We've set a temperature under which you can do experiments to get information so that everybody's doing it the same way. And it's basically what we consider room temperature. So the absolute standard thermodynamic temperature is the absolute measure of what? You're getting there. It's going to be the average total internal energy of an object or objects, namely its kinetic energy or energy of motion, which is, yep, there you go, kinetic energy, plus other contributing factors, and it's expressed in a number of what above absolute zero? Do we know?
Yes.
It kelvins. We're going to use Kelvin. Okay, and there it is right here. A typical thermodynamic standard state in a normal laboratory is 25 degrees Celsius. What is 25 degrees Celsius in Fahrenheit? Does anybody know?
It's probably like something 70.
It's right about 70. What's the temperature in this room right now? 68. So are we close to standard thermodynamic temperature? 68, 70, are we close? Yeah, we're pretty close. We're pretty close. So we can do it. Alexa, what is 68 degrees Fahrenheit converted to Celsius?
68 degrees Fahrenheit is 20 degrees Celsius.
We're a little low, right? But we're not super low. If this house was 45 degrees and the heat wasn't working, would we be anywhere near standard thermodynamic? No, that would not be good. So the standard thermodynamic state or standard thermodynamic temperature, we often call it STP. Okay, but it's not this STP, which you may see if you follow car racing. That is used in performance car racing. That's a brand that does, I think, lubricants and I don't even know what else. Or this STP. Anybody know the Stone Temple Pilots? Yeah. Some people call them STP.
That's fun.
All right, so what's entropy? All right, so we just talked about enthalpy. I'm going to give you a little touch about entropy because this is a little different, okay? They're very similar words, but it's different. Yeah, we're getting an ad, but at least they're no longer political ads. Yay for that.
You gotta make sure you're covered. I'm talking about.
Why did that-
investment in security.
No.
Believe me.
Go, there we go.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in the configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy. And again, start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small It just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
Okay, so entropy has to do with disorder and order and where your energy is placed. Skip to the next slide. Come on.
I think in lesson 15 or 16 we saw entropy is a disordered measure.
Yep. Yep. So this is a review from physical science, so it'll look familiar to you. But this is a quick review of thermal energy and heat. I don't expect you to have these answers because these weren't like directly in your notes, but if you think you know, you can take a shot at it. So a review from physical science of thermal energy and heat. And oh, isn't this perfect for this time of year? We might be getting some snow, so these guys are all bundled up. Thermal energy and matter. So temperature is the measure of the average, what we said, kinetic, everybody together for these, kinetic energy, the particles of matter. Thermal energy is the total energy of all the what? It's of all the particles motion, basically, right? Okay. Did it? We're good. All right, so she's doing her thing. She's fine. All right, so let's look here. What is the transfer of thermal energy from one object to the other? We talked about this. What's the transfer of thermal energy from one object to another? What is it?
Heat.
It's heat, right? And heat flows spontaneously from hot objects to cold objects. So thermal contraction and expansion. What is the increase in volume of a material due to temperature increase? Do you remember?
Specific.
It's thermal expansion. All right. When you're driving down the interstate, especially when you're going over a bridge and you're sitting in your mom or your dad's car and you hear the car going over these little strips in the road and it goes,
Oh.
you ever heard that?
Yeah, I have heard it.
You ever noticed that? Click, 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 click. Or when you walk on a sidewalk, is it one solid piece of concrete or are there little lines that break it? Why? What's that for? Because when things get hot, they expand. So if you didn't put those little rubber gaskets in the road for it to go click, 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 or if you didn't put those little spaces in the sidewalk, when the sun heats up the concrete or the asphalt or whatever you're dealing with, it will expand. And then it will crack if it has nowhere to go. So that's what those little rubber strips in the road are for. That's what that little the spaces in the sidewalk are for. That's all about thermal expansion. Anybody ever like do you know on your milk containers, if you ever look at a gallon of milk, on the side of the gallon of milk, sometimes there's like this round thing and it's pushed in. You know what I mean? Why is that there?
It's because when the milk gets spoiled, you can find out the milk.
Two reasons. If it spoils, it's going to produce gas and it's going to pop that out. And also if it gets frozen, it will also pop out because when water freezes, it expands. It's one of the few things that actually expands when it gets colder and it's only at a certain point. And only when it freezes, it actually condenses and condenses and contracts right until the moment it freezes and then it expands. But there's a lot of water in milk. All right. As thermal energy of a substance increases, its particles spread out and the substance expands. Thermal contraction and expansion. Thermal expansion is an increase in the volume of a material due to a temperature increase. Matter expands when heated. This is what makes liquid in thermometers rise. And it's the reason for the joints in the highway pavement that we were just talking about. Thermal expansion is also used in thermostats, many of which contain bimetallic strips. A bimetallic strip is made of two different metals which are joined together, and these metals are going to expand at different rates, one faster than the other. And if one side expands faster than the other, the strip will curve and operate a switch. So here's a video, but I have to give you a disclaimer. This is a rule for life. Never speak ill of this dude, Mr. Wizard, who's also known as Don Herbert, okay? He is one of my childhood heroes. Never speak ill of Mr. Wizard. Mr. Wizard is the best. Oh, there we go. Now, there's absolutely nothing wrong about random neighborhood children visiting a grown man's house all alone to learn about science stuff, because that's what this TV show was about. This was Canadian public television. So yeah, it's totally normal. They're just Canadian. But I watched this show as a kid, like every day, but these kids would just show up at his house. He was a neighborhood dude named Mr. Wizard, and he would show them science stuff. And it was totally cool. Yeah, she's just sneezing. So he's going to show you how a bimetallic strip works, which is really kind of cool.
On Miro, teamwork
Oh,
fast.
gosh.
New innovation workspace. Innovation belongs on Miro.
You recognize this, I assume, Dan, right?
Yeah, it's a thermostat that you put in your house to measure the temperature of the heat.
Well, you not only measure it because there's a little thermometer in here, but it actually turns the furnace on and off, right?
Yeah.
Well, you and I are gonna investigate what goes inside there, and it's based on the idea of a bimetal strip. Bimetal, meaning you know what bi means?
It means two.
Two, right, two metals. In fact, here are two metals right in front of you.
Yeah.
They're two wires made of metal. And I'm going to send electric current through them to heat them up.
Okay,
Heat it down and sight right across those weights that are on the top there.
okay.
And watch what happens as we heat up the two different metals. What's that?
Well, the one in the front, it's sinking down, like.
Right. Yeah. Now watch, I'm gonna turn off the current. Go back up again.
Same level.
As it cools off, it will go back up to the same height as the other one. In other words, what I did this for was to show you that metals expand, but different metals expand at different rates. Obviously, the one on the front expanded the most,
Yeah.
right?
Mhm.
Okay, now let's assume, I'm right over here, and light the candle.
Good.
And let's assume that we take two metals and put them together to form one strip, which is what this is.
Okay.
And light the candle. Okay. Okay, put it right down there. Now hold the strip right in the flame of the candle and watch what happens.
It's starting to make an arch upwards. It's making a really
See
big
how
arch.
it's going up?
Look how it's bending.
Yeah, bending a
Wow.
lot. All right.
Yeah, because of the heat.
Okay, now you can blow out the candle. Okay, now what happened was that looks like one metal, but it's actually two metals put together, like these two pieces of wood.
Okay.
Okay, now watch what happens if I expand the bottom. Watch what happens to the whole thing.
Oh, it's making an arch up right
Yeah, it
here.
makes it go up.
Yeah.
That's why that went up,
I see.
because the bottom piece of metal expanded more. Now let's assume we take this piece of metal and form it into a coil. Okay,
Okay.
so go around over here. I have a thermostat all set up on this little piece of wood. Can you find the coil?
Oh, there it is, I think.
Yeah,
It pulls
That's
up
the
around
coil.
there.
Right, there's the coil made out of that bimetal. And at the moment, notice that there's no current going to the furnace represented by this light bulb. So we want to cool off the room in order to make the furnace come on, and you do it here with this spray. Go ahead. Push down on the top, then out will come a spray of gas and you can cool off the coil. There you go.
Wow. it
On
comes
come the
up.
furnace, right? Okay, now this is the furnace. So turn on the blower and hold it at the coil. Okay, now the furnace went off.
Yeah, turn it off.
Now, this time let me handle it because I want you to watch right there, right at the end. See, I put a pointer here?
Yeah.
Right at the end of the pointer, watch right there. Right now, that's a switch and it's open.
Okay.
Watch what happens when I cool it off.
Wow, the switch moved down towards here and
Right.
it
I
expanded.
made it connected, right? Made a
Yeah.
connection
Mhm.
and sent current over to the furnace, which now comes on. Now watch what happens to the switch.
It moved up again and the current turned off.
Right. So now you know how the thermostat works. What do you call the thing inside? Bimetal?
Yeah.
Right.
So that's how that works. Go to the next page. No, go. There you go. All right, so we are going to have different scales, obviously, different scales for measuring temperature. Yeah,
Is it okay if I ask if Mr. Williams is still alive?
he is no longer. Makes me very sad. But no, he's not alive anymore. He was that age when I was younger than you. So, yeah.
I was just wondering.
No, it's fine.
I'm sorry for
No, it's okay. No. Hey, Alexa, when did Don Herbert, Mr. Wizard, die? It's been a while.
Don Herbert died on June 12, 2007 at the age of 89 years.
Woo! For Mr. Wizard, definitely one of my favorite TV shows of all time. So here we go. We've got different scales that we can measure temperature. This one is Celsius, right?
So
Fahrenheit, Kelvin, and then these two, Rankine and Ramuir, have very specific uses that will not come into play in any of the classes that I teach. So just know there are others, right? But if you look, you can see how things go. Here's your room temperature and your standard thermodynamic temperature of we said 25. So this is 69.8 Fahrenheit, 21 degrees Celsius, but it's 294.15 Kelvin. What happens at 0 Kelvin? Why is Kelvin even a scale? What happens at 0 Kelvin?
it doesn't go any more below.
Yeah, can we get to 0 Kelvin? 0 Kelvin is when all motion of particles ceases, which means all energy stops. Is that possible? No. So 0 Kelvin is like a theoretical thing. We can't reach it. We've never reached it. We don't expect to reach it, but it's important to have a point on a scale if we're aiming towards really slowing things down and really removing energy from a system. And if you notice, we use 32. We use this as our outdoor temperature and our indoor temperature. The rest of the world uses Celsius because they make sense. I saw one the other day. It said, if you want to remember how many feet are in a mile, remember 5 tomatoes because it sounds like 5280, 5,280.
5.
And then the response to it was, if you want to remember how many meters are in a kilometer, you just multiply by 1,000 because it wasn't made up by a crazy person, which makes more sense, right? All right, so Fahrenheit is used mostly in the US. Celsius is everywhere else and in science. Kelvin is used in physical sciences, which include chemistry and physics, but not biology, right? Not a physical science. We don't use Kelvin in biology ever. And then theoretical zero is where all motion stops, which isn't a thing. Specific heat. Specific heat is the amount of heat needed to raise the temperature of 1 gram of a material by 1 degree Celsius. Now, do you remember you had to use specific heat of water in your last lab? Your very last lab, you had to give me you had to use this number for specific heat of water, 4.18. These are known values, okay? We know these because they've been experimentally determined multiple times and they've been repeated and we know what they are. So you don't ever need to like experiment to find out what's the specific heat of iron. How much heat energy do you need to raise a gram of iron by 1 degree? You don't need to know that because somebody's already done the work. That's how it works. So calorimeters, you remember we did our calorimetry experiment?
Yeah.
And that those are used, they use the principle that heat flows from a hotter object to a colder object until they both reach the same temperature where you have equilibrium. So heat and thermodynamics, thermal energy and states of matter. Oh, don't we all want to be like this? Isn't this the weather we're hoping for? Aren't we all hoping for a little snow? Just
It hasn't snowed since I was 6.
yeah, it's been a good while.
Snowed like normally, like
So all the matter on Earth exists in 3 states typically, which is solid, liquid, gas. There's a plasma thing. Where do we see plasma? In lightning, in welding, things like that, you know, but it's not stable, right? We don't see it stable. Physical change from one state of matter to another state of matter is called what, people?
Called,
From one state of matter to another.
it's called temperature.
A state change or a phase change. Change of state, change of phase. Matter will change from one state to another if thermal energy is absorbed or released. If I put heat into ice, what will happen?
The heat will get transferred to the ice.
And then what will happen to the ice?
It will melt.
It will melt into water. So we've had a phase change because we have put heat in. If I take heat energy out of water, what will happen? It will freeze and it will turn into
Ice.
ice. Okay. Now, calorimeters again, they we need to keep in mind things like conduction, convection. This is the whole idea behind calorimeters and measuring these things. But conduction is the transfer of thermal energy with no overall transfer of matter. So conduction in gases is slower than in liquids because the particles in a gas collide less often, which is why if you if you mix hot water with cold water, you can put your hand in and like immediately feel a change in temperature. But if your heater comes on and starts blowing hot air into your house, it's going to take a while for your house to warm up, right? Because gas particles don't collide very often. Conduction is when things are touching. I know it's cold. Conduction is when things are touching. So if I touch the table and leave my hand there long enough, it will leave a warm spot on the table because it has conducted heat out of my body into the table. Then we have
Why is he
conductors.
outside the hole?
Thermal, I don't know, he likes it. Thermal conductors are objects that, or materials that conduct heat energy well or thermal energy well. They also tend to be good electrical conductors, usually, okay? And an insulator is a material that conducts thermal energy poorly. Is he covered in conductors or insulators, do you think? Insulators, blankets, shirts, these are all insulators, right? All right. Convection. This is when you have a transfer of thermal energy when particles of a fluid move from one place to another. So that is convection. So this is what happens in Earth's core. We talk about this in earth science. We have convection in the mantle, which causes our continental drift to occur. And it's also how your soup gets heated up in a pot. And it's why you have to stir it. Otherwise, certain parts of it get way too hot too fast. They will all get hot eventually, but it takes time. And convection currents occur when fluid circulates in a loop as it heats and cools. That is right there, a convection current. You see these globs of, it's not very hot yet because it takes a while to heat up, but those globs of wax, when they get hot, they will rise to the top. But when they get to the top, they cool down and then they will fall to the bottom where they catch heat and they rise to the top. Convection current.
It's like a cycle.
Yep. And then radiation, that's what we're all feeling from the fireplace. Radiation is transfer of energy by waves. So if we look at this image right here, what are we seeing? The fire represents what? Conduction, convection, radiation. That's going to be radiation because it's coming through waves. And that going round and round is going to be convection. And then why is he wearing mitts?
So hot.
Yeah, because it'll burn his hands because of conduction, right? Conduction, you'll conduct that heat right into his hands and that'll burn him. So in thermodynamics, these are important. I'm just going to read them to you. You don't have to really know these, but just know they exist because they'll come back up when you get to high school. So thermodynamics is the study of conversions between thermal and other forms of energy. Your first law of thermodynamics says your energy is always conserved. Well, that's also the same thing as the law of conservation of energy. Your second law of thermodynamics says energy can flow from colder objects to hotter objects only if work is done on a system. Did we say that earlier today? Yeah, earlier today we said if you want to take a warm object and a cold object, sorry, and heat it up, that'll work. But if you want to take a hot object and cool it down, you have to do work on it. And the third law says that absolute zero can't be reached, which is 0 Kelvin, which we said can't happen because that would mean, because if absolute zero could be reached, then that means this first law of thermodynamics would be wrong.
That picture reminds me of a picture of one Christmas.
They're snuggled up. Oh, yeah? Did you? Well, see, if absolute zero is reached, that would mean all the particles would stop moving. So that means that energy is not conserved, right? So obviously. And then we have this funny thing. We have first law, second law, and third law. And then we have this weirdness. What do you think is the next law? First, second, third?
Zero.
Yeah, zeroth, because that makes sense. I didn't make this up. But this says that if two systems are in thermal equilibrium with each other, then they're also, if one of them is in thermal equilibrium with a third system, then so is the other. So basically, if system A and system B are in equilibrium, and system C is in equilibrium with system A, then that also means system B is in equilibrium with system C. So heat engine, any object that converts heat into work, and waste heat is heat not converted into work. So there is a video that I have for you, but I'm going to leave it in your, in your resources list at the end of your email or for you to watch that talks about an entropy loophole. But know that entropy is central to the second law of thermodynamics, which states that the entropy of an isolated system left to spontaneous evolution cannot decrease with time. And as a result, isolated systems evolve toward thermodynamic equilibrium where entropy is highest. We're going to skip this entropy loophole and just show you that using heat. We can use it for engines, internal combustion, external combustion, heating systems, like in your house. This is a radiator. These use steam, and then that radiates heat, which means that it's radiation, right? We have cooling systems like heat pumps, refrigerators, and air conditioners. These are all things that add energy to a system to cool things down. You have to, well, not energy, work. You have to do work to remove energy from the system. Do work to remove the energy. And that's that, which is good because we have to get going. Let me bring these rest of these people in.
Hey, Eunice, do you have a Nintendo Switch? No.
Come on in, gang.